Verið velkomin á Málstofu. Við erum byrjað að streyma, þannig að við erum með í dag einn af okkar starfsmönnum, Pamela J. Hún ætlar að tala Innfjarðarrækju og eina sem ég ætla að segja er að hún er sérfræðingur á botnsjávarlífríkissviði. Botnsjávarlífríkissviði. Gjörðu svo vel.
Takk. Okay. Thanks for coming, everybody. I just first want to point out my co-authors who have been doing an amazing job at advising me. Bjarki has taught me all the technical stuff. I only started working here, a bit over a year ago, so he's taught me a lot of the technical parts of the model that I'm going to present. Inga has been advising me again and again on the biology of shrimp. And Mugger, thanks for hiring me, because the first thing, even in the interview, he was saying, what is your interest in multi-species modeling? And I said, oh, I think it's great. And he said, great, you're going to do shrimp. First thing. So here is where within fjord shrimp stocks are located across Iceland. I have Ísafjörður and Arnarfjörður pointed out because those are the biggest in-fjord shrimp stocks there are that are currently fished. And they're the ones that I'm going to be focusing on today. Generally, they're important historically. There's almost been a century of shrimp fishing in the West Fjords. Peak landings were around 850 or so tons in Arnarfjörður in 1994 and closer to 3,000 tons in Ísafjörður in 1990. And surveys date back all the way to the mid-1960s. They're still, however, important locally, especially because it's one of the few kinds of fishing you can do within a fjord. You can use a small boat and go out in weather that you wouldn't be able to go at least with a small boat, out beyond the fjord with. But recent decades have been marked by decreased biomass indices and fishery closures. This is despite consistent surveys and management, so you know better than me probably how popular these, management of these stocks are. So Arnarfjörður and Ísafjörður, these are actually from last year's reports, but generally this is just to show the general trends of catches. You can see that there are periods of fishery closures in both places. Generally the index has a downward trend. Ísafjörður has come up a bit in the recent few years, and F-proxy is following that trend as well. In-fjord shrimp management is conducted like this. Survey indices are calculated first from two annual surveys. One that, in this talk, I just call it the hoist survey and vetter survey. And then generally from these, an advisory rule is applied to a reference biomass index to determine the catch. But it may be modified according to ICES guidelines regarding using the precautionary approach. So in Ísafjörður, that would be, you take the survey biomass for the year, multiply it by this 0.5. That 0.5 is considered an F-proxy, sort of the target for fishing mortality. And then from that, you get the TAC of the next year. And the same in Arnarfjörður, except that the rate is 0.346. However, there's no absolute biomass estimates, and it's not popular because of the decrease in biomass recently, and it ends up being contested quite a bit, especially since the fishery closures. So what I'm going to present today is a precautionary tale about the intertwining nature of estimation of biomass and catchability, environmental effects on growth and mortality, and optimization difficulties. So this is a work in progress. Don't expect me to come up with the right answer at the end, but I'm getting closer every month. And the problems are quite big. This is the first problem is that we're talking about invertebrates. That means there's no good quantitative age data, and age data is really helpful in nailing down population dynamics. So all invertebrates, when they don't have good age data, are very difficult to estimate biomass levels using population dynamics models. Growth is by molting, which means it's a very discontinuous process. happens suddenly once or twice a year. Growth is also sensitive to temperature because they're invertebrates, again. In this case, the connectedness to offshore populations is rather unclear in a lot of cases. They tend to aggregate, and they are food for everything. So this is an example of how aggregation has increased over the years. Note the years jump from a 1988 to 1991 series. This is from Inga's reports here, but jumps from 1988 to 1991, and then to closer to the present, 2012 to 2015. And you can see that the catch has been kind of becoming consolidated in just a few small areas, but the size of the catch is quite big, and that prevents catch per unit effort from dropping, which also means that the fishermen over time might say they're quite easy to catch, there must be a lot of them, but it's not necessarily the case if the distribution has changed as well. On the other hand, cod stocks are doing great. So this is from the 2017 report as well. You can see the harvest rate has decreased quite a bit, and biomass has gone up quite drastically in the past decade, I'd say. And cod love eating shrimp, at least when they're in the fjords. So this is diet data from Jónsdóttir et al. 2017. Cod, here on the left you have cod. Notice the purple is Pandalus borealis, and it makes up quite a bit of the gut content data that's available from 2000 to 2015, and then some of the other species involved are haddock and whiting. Temperature changes may affect growth, and this is sort of a rough picture of temperature, bottom temperature and surface temperatures are in Arnarfjörður, but you can see there's a general trend upward, at least with surface, and possibly the same with bottom, with some missing data in between. So the motivation for this is what is causing shrimp declines. Could it be environmental or could it be fishing related? Not 100% sure. Also, is the advisory rule sufficient and not overly conservative? That's the criticism that we get from stakeholders. But to answer these, we also need to ask the more technical questions. Can biomass be estimated? And what effect do environmental variables have on the biomass? And finally, we'd like to get to the question, which I'm not going to get to in this talk, how do the advisory rules perform under uncertain biomass levels? So the overview of this talk is that I'm going to explain the operational model and data going into it. I'm going to talk about trying to find the best model from a very over-parameterized state. That just means that there's so many details going into the model that there could be a lot of right answers. So to do that, I'm going to look at a few likelihood profiles and then describe the upcoming management strategy evaluation that will try to get at the effectiveness of the advisory rule. So the operational model is a size and age structured gadget model. It contains lengths that are 0.3 to 2.5 centimeters in 0.5 centimeters bins. The ages are 0 to 8, and there's no stock recruitment relationship per se. There's just recruitment is estimated each year. We'd like to look at whether there's a stock recruitment relationship sort of as an output after the fact. There are commercial fleets in there for Arnarfjörður and Ísafjörður, but we also have included predator fleets, which are basically cod, haddock, and whiting in a few different size categories. And these predator fleets are basically scaled. The model will help to scale to see. We estimate the effect of the predator on the stock by having sort of a scalar against predator biomass index, and that biomass index is coming from the shrimp survey. So we have, if we catch a bunch of cod at the same time as we're catching shrimp, we don't know how strong the effect those cod have on shrimp, but we have a time series at least of how many shrimp against cod there are in the survey. And so we're doing that for a few different species and a few different size classes. I also included a positive linear effect of temperature on the growth parameter K, and K controls how fast, especially when they're young, the shrimp grow. That's in a length-based von Verdelanffy growth model, and I'm using two measures of temperature, surface and bottom, from the shrimp survey. So here's a schematic of how the model works. I actually have both fjords in the same model. They're separated by area, and they're separated as two different stocks. So these two stocks have immature and mature components. The immature mature into mature components at separate rates. And there's recruitment here, but it's not functionally in the model. It's just, that's going to be an output. Growth for immature have a couple things in common between the areas, and that's to help estimation, because Árnafjörður has pretty good data, but Ísafjörður data is a bit confusing. So I'm trying to use, by including them in the same model, I'm trying to use some characteristics of Árnafjörður to help nail down the population dynamics of Ísafjörður. So one of those is that they have the immature have the same L infinity in the von Verdelanffy growth model, and they also have the same effect of temperature on growth rate on the K, but they have different Ks. So they can grow differently, but they have to respond to temperature in the same way. They have the same growth when they're mature, and the same natural mortality, and they have the same effect of predators. They have different predators because it's just the local predator biomass index that we're using in each location, but the effect is the same. So in effect, that would be saying that a cod, 10 cod to a ton of shrimp has the same effect as 10 cod to a ton of shrimp in both places, in Árnafjörður and Ísafjörður. And we also have the same selectivity across all commercial fleets and the surveys. So the data that we're using are survey data from from those two surveys that I mentioned, in 6 slices of length classes. So we have 6 different survey indices that vary by sizes. We have proportionate length data from the surveys, proportion mature at length from the autumn survey, and then mean temperature across survey readings for a given year, both in bottom and surface. We also have commercial or other samples, just whatever I could find that could be proportionate length from each location. Relative predation effort is represented by the predator biomass, and that's, as I described before, cod, haddock, whiting in 3 different size categories, but they're all scaled by a single estimated scaler to have the same effect against the shrimp. Landings are incorporated directly, that is, landings are removed from the population directly, and it's fit using a sum of squares resulting in a likelihood score, iterative reweighting, and mainly simulated annealing, which is supposed to be a good global optimizer that can deal with lots of local minima. So the best model, so first, just to show you the method that I'm using, I'm going to show some preliminary results from a preliminary model that was based on only Árnafjörður. And then after that point, I expanded this model to include both Árnafjörður and Ísafjörður. But I can at least use Árnafjörður results are a little more clear, so I'd like to just describe the methods that I'm using with that, and then I'll show you some results from the developed model. So some properties that I'm finding from the preliminary model. Okay, first thing, before I say that, natural mortality in shrimp is also, natural mortality of anything is not well understood. But in shrimp, it's also even more, less understood, because you can have a wide variety across all different kinds of shrimp species. So for this species, not very far away in the North Atlantic, I saw a report that said natural mortality in their assessment was using around 0.75, but then from their study, they should bring it up to something like 1.25. So obviously, and this is quite, a bit different. Other natural mortalities could be quite a bit lower than that. So the first thing I wanted to do with this model is test whether I could detect a best model, but I wanted to vary natural mortality and then fit a model at a variety of natural mortality values and see if I could find a best model based on varying the natural mortality by hand. That's called a likelihood profile, and that's what this is. So each point is a single model optimization at a natural mortality level. And you can see there's a nice curve here with a minimum, which is nice because then you could say, okay, the natural mortality of 0.39 fits the model best. Remember, in this model, it's a little more complicated because my predator fleets are actually natural mortality in a way, what you would count as natural mortality in a model that does not have a predator fleet. So if you, so you can see that this is the same M and the same models per point, but as M goes up, you get less of an effect of the predator. This is the scalar that you get from the predator fleet. So at high levels of M, you cannot have predation happening, which is good. That's what you would expect, because that just means that down here, you can have both a constant natural mortality going on through the years, as well as a reduction based on predation. However, when you look at the biomass estimates coming out of this model, things don't look so good, because this is the same best model that we were talking about. However, the biomass estimates, this is for 2017, on this side, are very low, and you go one model over, tiny difference in natural mortality, and suddenly you get a huge biomass. So there's something very difficult going on with the optimization of this model. So, to tackle this, I decided so in these cases where we have very high biomass levels coming out, what that means is that the catchability is not known for the survey. It's not well estimated. We have no idea from the data. They could be scaled up and down. The survey indices could be scaled up and down as much as you like, and there's really not much information. Or the optimizer's not finding the right answer. So to see if the optimizer's not finding the right answer, I would scale the upper bounds for what biomass could be. Those are the recruitment upper bounds, and tried a variety of values. These are quite high, but if you force it to go lower and lower, then the biomass levels would also be forced to go lower and lower. And then look at the likelihood scores of those to see if I can find a better fit to the model. And this is the kind of thing you would get from that. So here, this is the recruitment upper bound. So the biomass coming out of it is very high up here, and it goes down over here. So here you get a very slight minimum. Basically, a lot of these models are the same, and it's just showing that, again, it's very difficult to get an idea of catchability from this model. So there's very little information regarding absolute biomass. However, perhaps there's some other information we can start to narrow down the range of possibilities. So can resulting stock recruitment relationships and predation levels be used to narrow down it to the right answer, just using our general knowledge of the system? Because obviously, this is corresponding to thousands and thousands of tons of biomass. It's not possible that a fjord that small would hold that. So we do have a range of believability. We just need to look into what the model is trying to tell us about it. So here are stock recruitment plots over a range of sort of the upper bounds of recruitment. So the top left has a very low biomass. The bottom right has a high biomass. And you can see in the top left, actually the top left all the way, into here, it looks like what you would sort of expect from a stock recruitment relationship. Those lighter points are more recent, so you have, small biomass and small recruitment coming out of it. But once you get up here, it gets quite fuzzy. Here we have what comes out of those same models in terms of the level of shrimp being removed by the commercial fleet versus the predator. So you can see up here, the top left, the predator has no effect. You only have the fleet operating. as you progress with higher and higher biomass, you have the predator taking the most out of the shrimp population. So here reflects our belief, a belief that the population is being completely controlled by predation. Up here would be the population dynamics are being controlled by the commercial fleet landings. That, or at least the decrease is being controlled by, one or the other. And somewhere in the middle is probably more like what we would believe. So those were the results based on just Arnarfjörður. It gets a lot more complicated when you double the size of the model and add a whole nother fjord in there that does not have as good of data. And so I'll just show you some preliminary results from the best developed model. This is a starting point for a management strategy evaluation, so I'm taking my time trying to make sure that I get quite a good model at this point, so that the rest of it is not, I'm trying to think of a word that's not offensive. Okay. Anyway, so this is the same kind of graph that we were looking at, but graphed slightly differently with the commercial fleets as well as the predation. This is the best, after going through a similar routine as I did with the Arnarfjörður model, I came up with one model that seems to be the best so far. So we're just sticking with that for now, although I do need to check this model and run a few other likelihood profiles to see if the optimization is actually good for this. So far it looks here, the green is the Arnarfjörður commercial fleet, and this green is the Ísafjörður commercial fleet. And then all these other colors are some predator. These are whiting, haddock, and cod in 3 different size classes. And so those, anything besides the green, when those add up, that means there's a lot of predation going on in those years. But you can see that the general scaling of these is that the commercial fleet in Arnarfjörður is entirely dominant here, but the amount of shrimp being removed by the predators in this region is almost about the same as the commercial fleet until you get a fishery closure, then it's all the predator. And then you come back here and it's about the same level. So predation and the commercial fleet are both contributing quite a bit. Ísafjörður has a different story. Ísafjörður looks like it's mostly the commercial fleet with a small contribution of the predators, and then you have this fishery closure, but after that it's both the predators and the commercial fleet are contributing quite a bit to the mortality of the population. And one thing, there's a couple things about this model which also make me think we're getting closer to the right answer. One is that the growth coming out of it, Ísafjörður and Arnarfjörður are both plotted here. These are the growth that has been produced by the model. So we have 3 lines for each of them. The middle line is the mean. The upper one is the 95% confidence interval, and then the bottom is the lower of that. And so we have Ísafjörður kind of going up like that, Arnarfjörður over here. This is after 2004 and this is before. But before 2004, you can see that there's a bit of an offset here. It might be a little bit difficult to see. The red line is almost the same as the upper of the blue lines. And if you look at where these are landing, that means that the Ísafjörður, let's start with Arnarfjörður. The Arnarfjörður, the mean size of an Arnarfjörður 2-year-old shrimp is about the same as a Ísafjörður 1-year-old shrimp. So Ísafjörður is growing quite a bit faster. Inga, I hope you don't mind me showing this. It's her figure from something that she's working on. But here you just see the same pattern, which is very good because it's not easy to get these growth curves, and there's been been years of work trying to get something generally that looks like you might have a growth curve that makes sense, especially if these are changing between fjords and you don't have a reliable way of aging the shrimp. So this is what Inga's preliminary work is showing with Ender. Yeah. So here you have the same thing where Arnarfjörður shrimp at age 2 are about the same as what you would expect from Ísafjörður at age 1. The other thing, I'll just go through these, briefly, but the indices that I'm using in this model, the general pattern corresponds pretty well with the indices that are currently used for management. So this would be, the top one is the juvenile index, comparable to the juvenile index, and the bottom ones are more comparable to the female or fishable biomass indices. And that is for Arnarfjörður, and we get sort of a similar trend with Ísafjörður, except notice when you put this into a model, you can see, the juvenile, this is part of the reason why Ísafjörður is so difficult. When one year you get twice as much, the numbers bounce around a lot. So by using all of the data in a model, you start to try to get a trend out of that, and this trend shows that it sort of ignores the upper points as the best fit to the data. So these are the stock recruitment plots that come out of this as well. Arnarfjörður has a similar pattern as you saw before, so the model hasn't changed that much when we added Ísafjörður. Ísafjörður has sort of a nice curve that you can see. The oldest years, are out there, and the youngest years, the most recent years are over here. And of course, we want to know what the biomass estimates coming out of a model like this are, and how they relate to the advisory rule that we have in now. So here is a plot with Arnarfjörður, the mature Arnarfjörður is the blue line here. The mature Ísafjörður is the purple line, blue and purple. And these are just the 2018 values for biomass. These are very, very low, actually. That means that this number for Ísafjörður biomass levels corresponds almost exactly to the index, which is really good because that means that it's good for on the management side because that means that Q is about 1, and that's sort of an implicit assumption about the management system because this means that applying the 0.5 proportion to this would result in a F value around 0.5.
Pamela,
Yeah.
could you please speak at the microphone? We're recording you.
Oh, sorry. Sorry. Okay, and the Arnarfjörður has a different trend. The Q is closer to 0.3, which means that it would be considered a conservative harvest control rule, more conservative than intended. However, this Q is not the whole story because those harvest rates coming out of the advisory rule, we don't know the actual effect of the rule of those harvest rates on the population. And that's what we would get from the next step, which is the management strategy evaluation. So this is good. This is sort of confirming that generally the strategy that we've been going on is in the ballpark regarding biomass levels, but we're still not sure if the harvest rates are ideal for each population, especially given that the predation has been quite high in the past decade or so. So the future management strategy evaluation that I'm planning to do is that first we'll take a subset of models that have believable biology, so not just that one, but the ones that also have comparable likelihood scores. Add in some future variation, which includes observation error, recruitment error, so we'll fit a stock recruitment relationship to the output, but then say, okay, it's not going to be perfect recruitment every year, and add in some error. There will be error regarding the predation levels that are going to be expected. Can't exactly predict those very well. And also error in the assessment itself. Those will generate a variety of possible futures through simulations with the current advisory rule and then potentially other advisory rules that we try to create. For example, we could include predation index in the advisory rule itself. And then hopefully from that management strategy evaluation, we'll be able to evaluate these advisory rules based on the resulting productivity level of the stock, as well as the risk of the stock going below a certain level. So the conclusions from this, they're not, fully complete yet. I have a lot of work ahead of me still, but so far we see that the true ecological state is a state of over-parameterization. We can't really get around that. That means we should take care in choosing how the model choices, we should take care in choosing how we construct the model, because it will constrain our belief in the ecological states. This was a useful exercise despite the difficulties in estimating catchability, especially because the need to look, this whole problem with optimization, it's probably not just the framework. I sort of think that this is going to be a problem in a wide variety of scenarios, so it's good to look into why we're not getting the right answers, because that's really slowing us down if we need to do a lot of likelihood profiles. So, all right, thank you for listening, and please let me know if you have any questions.
We have time for questions, but please use the microphone.
Any questions? Steve?
Well, thanks, Pamela. You clearly have your work cut out for you in trying to solve this one. So there was a few big issues, of course, and one of them is catchability. I mean, there are published estimates of shrimp catchability in other places. Are you able to constrain catchability outside of the model and then?
That's a good point, and that is something I always meant to do, and I never did. It's a very good point, but I have a feeling that even if I got an estimate, I'm not sure I would believe it, because the shrimp are so difficult to estimate to begin with, simply because they're invertebrates. So I think it's sort of like mortality here. The mortality estimates that they were approaching were in the report of a stock nearby was, 0.75 was a reasonable mortality, they thought, and then they thought, wait, it's probably closer to 1.25. That's even beyond the range of this model, because this model wouldn't work with that high of mortality in it. So I think, I agree, I need to look that up and see how close these are, but I would be suspicious, because it seems like shrimp stocks are so flexible to begin with.
True, but I would have thought that the catchability in the two fjords would have been similar, with the exception of the amount of untrawlable bottom. And I don't know how much.
Yeah, that's a good point.
So if you can quantify that, that should be, quantifiable outside of a model. And then if you assume, similar catchability between the two, except, excluding the untrawlable bottom.
Yeah.
And as for mortality rate, I mean, usually a lot of these models, everything just scales up, right, with your choice of M. So is there any problem with sort of assuming a constant M between the two, maybe a temperature dependent M?
It could, yeah. Okay, wait, start with the first one.
Yeah. So the catchability, yeah.
Yeah, the first one, the catchability between the fjords. The two fjords, okay, so the way the results that I showed you right now are quite preliminary, because another step that I need to do, since I have both fjords in there, is that I think all of the scaling between, including biomass, is also dependent on the predation level. So you're right, so you know how the natural mortality will scale with biomass. In this model, we also have the problem that the effect of predation will scale with the biomass, which means that the two are interacting along with biomass. So because natural mortality and the effect of predation are different, but these two fjords are able to scale slightly differently in terms of biomass levels. And I think it's because of the incorporation of predation, and that's basically another likelihood profile that I'm going to need to look into. The second question.
You know what, there's so many, it's just, yeah. We'll pass it on.
Thank you, Pamela, for an interesting lecture. I just have a very simple question, different from Campana. So why do they grow differently? Like, why do they grow faster in Ísafjörður compared to Arnarfjörður?
I will defer that temperature.
So is it warmer in Ísafjörður than in Arnarfjörður?
Yes.
Really? Okay, that was surprising. Okay. I promise, I said it's going to be simple.
Yeah, thank you very much for this interesting talk. And I understood that it's really difficult to come up with a viable model. There are 2 points that I found particularly strange or whatever. One is when it's so difficult to estimate the absolute biomass of the shrimp, but you have the catches, and but isn't it more easy to estimate the biomass of cod and other fish in the fjords, and then come up with a reasonable amount of predation that these fish are causing? Because you showed some different studies, some of them with very little predation from fish and others with huge predation from fish, and yeah, maybe that fish biomass would be helpful. And then, sorry, the other question, in the end, where you showed the time series of the developed model with shrimp biomass for the fjords, even though maybe in the last years these biomass appeared to be realistic, but in 1970 to 1980, the biomass in Ísafjarðardjúp was something like more than 50,000 tons or so. Is that realistic, or is it an effect of oversensitivity of some model parameters?
I should have, okay, let me do the second question first, and the first second. The second question was that I should have plotted not the results before the data were available. So that is sort of like a burn-in period where just allowing that amount of flexibility. So the model mainly start around 1988. I'm sorry, the data mainly start around 1988. So those, from that point is when I would trust the model results. Because before that, allowing a period of the model to run with no data simply allows the model to sort of back calculate what the best scenario would be before that to best fit the data beginning, around 1988. So the period before that, the decade before that, from maybe 1978, is setting up the values of 1988, and before that, it's all over the place. So I would not trust any of those, before the data started around 1988. The other question, can you?
Yeah, that was when you don't know the biomass, the absolute biomass of the shrimp, but you know the catches.
Essentially,
and do you know the biomass of the fish?
Yeah, essentially that's what I'm trying to do in this model. But the problem is that the biomass estimates are not. There's not that much data actually for those biomass estimates. So it would be very difficult to reliably come up with first the biomass biomass index for the predators by themselves in a reliable time period, reliably over the time period. The other thing is the diet data are quite sparse. So for a given species, diet data are just very difficult to deal with because it's one snapshot.
And they had quite some scatter between years.
Yeah, there's a lot of variability in them. We don't have that much of them, and there's a lot of other ecological things that could be going on between Ísafjörður and Arnarfjörður.
Okay.
Thank you, Pamela. It's very nice to see how much you have progressed since the annual science conference in Hamburg. Good work. I'm just wondering, you say that, given that the advisory rule that we are using now is more or less in the ballpark of something sensible, and your estimates of Q from it, even though you say we should take them with a pinch of salt, the advisory rule in Ísafjörður is now 0.5 of the survey biomass, which you say is kind of okay. but it used to be 1, which basically means that we caught all the shrimp in the fjord in the past. Isn't that a bit of a, bit strange? So possibly what I'm kind of referring to is the Q possibly kind of overestimating it in the model.
Yeah, it very well could be. So, so part of Steve's question was sort of like how allowing the differences between Arnarfjörður and Ísafjörður. There's a certain balance that I'm trying to get in this model of gaining biological information from Arnarfjörður so that it informs Ísafjörður without overly constraining Ísafjörður. And and it could be that that's going on. So it was it's in the ballpark, but that is a really low biomass estimate for Ísafjörður, if that's true. So I guess I would hope it's not 1 then, if in the past it was 1.
Okay, I think this is enough for Pamela today,
Yeah.
right?
Yeah.
You want to say it?
No.
No? Okay.
I'm good.
Thank you, Pamela.